Okay, hello, IB Math people. Today I'm going to be talking about vector equation of a line, which we already learned about in class, and you've done some homework on it, but it's time to put it into our notes. And then we're going to do a couple of new things. We're going to talk about velocity equations, and we're going to be talking about what else? Velocity equations and unit vectors. Okay, so let's first start by writing down the things we already know. So this might not look very familiar, but this is the vector equation of a line the way that it shows up in your formula packet. Okay, so here it is in the formula packet. And the way that we've been writing it and our textbook writes it is a little bit different. So we're going to write that down. But I wanted to let you see how it shows up in the formula packet. And the only difference between how they write it and we write it is this letter right here. They're using, I think this is the Greek letter lambda. I'm not sure. But our textbook, we use the letter T, or you also see us use the letter S. Okay, the letter T is handy because when we talk about velocity, T represents time. Okay, so I'm going to talk a little bit more about this letter here and what it represents. But R, A, and B are vectors. R and A are position vectors, and B is a direction vector. All right, I don't think I like this pen after all. I was going to try and use different colors, but I really just like my purple pen. All right, so we are going to be using this one. This is what we've been using with our textbook. We've been using the letter T, but like I said, it can actually be any letter, okay? But can be any letter. Can be any letter. And it's a scalar, okay? It's a number that you multiply with the vector, okay? It's just a scalar. So a number that we multiply with the vector, all right? Okay, so what we learned in class is that A is the position vector of any point on the line. Okay, so that letter A there, A is the position vector of any point on the line. So we get to choose. So we get to choose a point that's on the line and make that A. So it's really similar to the letter B, or the y-intercept in y equals mx plus b. Okay, so similar to B, except B has to be the y-intercept, but here A can be any point as long as it's on the line. So it's similar to the B value in y equals mx plus b. Okay, so you can kind of think of it as sort of the equivalent. It's like your starting point. This is where you're going to start. Okay, and then the B, this is a direction vector that tells you how you're going to move. So how to get to another point, to the next point on the line. That tells you how far in the x and y and z directions, if we're in 3 dimensions, to get to another point. On the line. So this is similar to the slope. Okay, so as we saw when we were doing the activity in class, this is really like exactly like the slope. So it's your rise and your run, except that the it's run and then rise. Okay, it's just upside down. All right, so let's put an example into our notes. So if I have R, vector R, position vector R is equal to 1 comma 3 plus t times the direction vector to 1. Okay, so what is this saying? This is saying start at the point 1 comma 3. Okay, so this is a position vector, which is basically the same thing as coordinates. So start at 1 comma 3 and move 2 units right and 1 unit up. Oops. I should have just used the numeric letter. Sorry about that. 1 unit up. Okay, so if I go ahead and try graphing this, and where's my straight edge? There it is. So if I go ahead and graph this, I'm going to put on the point 1 comma 3. So 1 comma 3, there's my starting point. And then I'm going to move 2 units to the right and 1 unit up. And that gets me another point. And I could do it again, 2 units to the right and 1 unit up, just like slope. 2 units to the right, 1 unit up. Okay, so now the thing that's kind of weird about this is we don't fill in anything for t or r, right? But, oops, sorry, you can't see what I'm looking at now. I just graphed it. All right, so we have, this is like our b and y equals mx plus b, and this is like our slope. This is like our m and y equals mx plus b. And we leave just the t and the r vector just the way they are. But what if we wanted to know, well, what is this? Well, it's kind of like the x and the y in our y equals mx plus b. I could substitute in a number for x, say, you know, like 1 or 2 or 3, and then I could figure out what my y value is going to be. So I can do something similar here. I could say, okay, what happens when t is a certain number? So let's say, where'd my cap go? Let's say t is equal to 3. So what happens when t is equal to 3? So when t is equal to 3, what that means is I'm going to move this number, these directions, I'm going to do it 3 times. So if I'm starting here and t is equal to 3, that means I'm going to move in this direction 3 times. I'm going to go over 2, up 1, over 2, up 1, over 2, up 1. That's 3 times. So when t is 3, I'm making this move 1, 2, 3 times. Okay, the actual vector is a straight line. So let me go ahead. The vector equation of a line, I should say. This is a line. It's not a vector. I've created a line. Here's the starting point on this line, and then here's the direction. So if I'm saying that if t is equal to 3, where do I end up? I'm going to end up here. I'm going to move this amount 3 times. So that would be, where am I? If I go here and I go here, let's just read that off. 1, 2, 3, 4, 5, 6, 7. So I end up, when t equals 3, that means that r is going to be equal to, what did I just say? 7. And what was this? 1, 2, 3, 4, 5, 6. R is going to be 7, 6. But notice that's also its position. So that's also, this is r as a position vector. It gives me the position of another point on the line. Okay, so we could have done that algebraically as well. We could have said, okay, r is going to be equal to 1, 3, plus, I said t was 3, times 2, the vector 2, 1. And so you can see I can do 1 plus 3 times 2. 3 times 2 is 6. 6 plus 1 is 7. And 3 plus 3 times 1, well, 3 times 1 is 3. 3 plus 3 is 6. So there it is, okay? So we could put in, you know, we could make like an XY table, except it would be a TR table. We could put in values for T and figure out what is going to be the position of R, okay? And it gives us the position vector. So we can do it algebraically, or we could do it by graphing. So just like we can do it with y equals mx plus b, you know how you can make an xy table and just pick numbers for x and figure out what y is and then plot those points? You can do the same thing here. Pick numbers for t and figure out what the r is going to be. Or vice versa, you could pick numbers for r and figure out what the t is going to be. Okay, so a lot of similarities to y equals mx plus b with this equation, vector equation of a line. All right, moving on. We also learned there are other ways of writing the vector equation of a line, so we can write it in slightly different forms. So I'm going to give you an example, and then we'll just write it in a bunch of different ways. Okay, so different forms. Of a vector equation of a line. All right, so for example, if I gave you r equals, I'm going to do it in 3 dimensions, 1, 2, 3, plus t times 4, 5, 6. I could write that as, okay, so I'm just going to write it a bunch of different ways. I could write that like this. I can write it out in component form, x, y, z is equal to, and then this part is just going to be the same as it was above. We're going to work our way into parametric form is where I'm going to be heading with this, if you remember that from the activity we did in class. Okay, or I can combine these parts together. So I could say my line is equal to the components x, y, z, such that the x component would be 1 plus 4t, so I'm doing t times 4. The y component would be 2 plus t times 5, that would be 5t. And the z component would be 3 plus t times 6, or 6t. Okay, that's another way of writing this equation of this line in 3-dimensional space. Or we can write it in parametric form. Okay, so or parametric form, which is where we actually separate the 3 equations, one for x, one for y, and one for z. So parametric form is where we separate the x, y, and z parts. So we could write x equals 1 plus 4t, y equals 2 plus 5t, and z equals 3 plus 6t. So we're separating out the different parts of the vector, the x direction, the y direction, and the z direction. Okay, so you could also take parametric form and write it as a general coordinate. So you could write the x coordinate like this, and then comma, and then this is the y coordinate. And it's understood that this is the x, this is the y, and the last one would be the z, because we understand how to write coordinates. Okay. A little bit of extra information which would help with the homework. So if you haven't finished the homework yet, if you want to find the angle between 2 lines, we don't need the entire equation of the line. Okay, so here's my line. If I have another line and I want to find the angle in between, oops, sorry, you can't see that, and you want to find the angle in between the 2 lines, you don't actually need the entire equations of the lines, because if I take these 2 lines here and I move them to somewhere else, like over here, the angle in between them is still going to stay the same. Or if I move them up here, the angle in between them is still going to stay the same. So it doesn't matter where they start. This point doesn't matter at all. The only thing that matters is going to be the slope part of it, which is the direction vector, this part right here. So if you want to find the angle in between 2 lines that are written in vector form, vector equation of a line form, if you want to find the angle in between them, you only need to use the direction vector part. That's the b. Okay, so let's just go ahead and write down a little example of that. So this is kind of like a little bit of additional information. I keep having to move my, let's see if I just move the camera instead. Okay, so a little bit, kind of a new thought. If you want to find the angle between two lines. Use the direction vectors. Okay, so that's the B part, the B vector, okay? So, for example, if I have R is equal to 1, 2, plus T, 3, 4, and I have another R, another vector equation, which is 5, 6, plus T, can you guess what I'm going to write? 7, 8. Then when we would use the formula cosine theta is equal to U dot V over magnitude U times the magnitude V. Our U would be equal to 3, 4. That's the direction vector. And the V would be equal to 7, 8. Okay, I'm not going to do the whole problem. I'm just going to tell you that's how you would get started. Okay, so it doesn't matter where they start. Doesn't matter where the line is starting, that starting point. All that matters is the direction vectors. Okay, and then you can use those to figure out the angle in between. And don't forget, if U dot V is equal to 0, okay, if you were to dot product these and you got a 0, remember what that means? They are perpendicular. Okay, and then also remember, if one is a multiple of the other, notice 4 times 2 is 8. So 3 times 2 would be 6. If that had been a 6, then we would know that these lines are parallel to each other. And there's a possibility they could be the same exact line. They could be the same exact line. So if they ended up being parallel to each other and they went through the same point, like you could plug in a point here and figure out that they both go through that same point, then it would be the same line. I believe there was a homework problem like that for you to look at. Okay, moving on. So that's the stuff we've done. And now the stuff where we're going, new stuff. Actually, you know what? I think I'm going to stop this video and make a second video for that. Okay, so those were the notes on stuff we've already done. Okay, so vector equations of a line. Oops, I need to stop the recording. Here I am. I hope I don't get in trouble for being in The Simpsons.